Good day. Today I want to talk about a work that we have published last year, and it is about quantum computing. In particular, it is about simulation of stochastic processes. Indeed, the title of our work has been coined to be Quantum Enhanced Analysis of Discrete Stochastic Processes. It is by my collaborators Daniel Park and Francesco Petrocione. And with quantum enhanced, we mean that we also do a lot of classical work. So we just use the quantum computer for a little bit of computation. We want to estimate the expectation value of a discrete stochastic process under the transformation f. This discrete stochastic process, Sn to be precise, is a sum of increments. Each of these increments have up to k realizations, and they can be either independent or dependent. They must not be of any explicit type, so they can be very general. Indeed, when we talk about this here, we are interested in such processes that resemble, for example, a Brownian motion or a discrete version of it. We show that we can estimate this expectation value with a variance that actually is independent of f of Sn using a quantum computer and Fourier series. Indeed, if we look into this a bit more precisely, we say that if we have a Fourier series of a function f, we can compute the expectation value as given in this way using characteristic functions. And to be more precise, it's going to be about evaluating the characteristic function. When we have the characteristic function, which is essentially what we show we can do, we can use it and reapply it over and over again with different Fourier series of the function. Now our work is divided in two parts. The first part is about state preparation. Indeed, we want to show that we can create the full probability density function of a random variable constructively. In the second step, we talk about measurement. An approximate characteristic function with an error independent of the random variable is calculated and then used. The state preparation that we're talking about, we also call it a quantum brute force approach, because all the realizations of this stochastic process are realized in the quantum state. It is, however, the measurement that we will need to scoop up all the information, summing it up and getting an approximation by measuring an expectation value of an observable. So now talking about the state preparation, we repeat the discrete stochastic process with a sum of increments, and we want to encode it into a quantum state. The quantum state that we are interested in is the sum of all paths of all the realizations that we can find in front of it with the square root of pj. Pj is simply the joint probability of all the increments being at a certain path. It is the joint probability, and in essence, if we look at it, it's the probability density function. On the other side, we also have a green unitary that is being parameterized by the path of the realization, and it's applied to a single qubit. The single qubit is interesting here because now we point out the realizations. So we have one part that has the probability, joint probability of a realization, and then we have a second part where the realization is somehow manifested. Well, to encode the PDF, we can use this kind of approach. When we have a process that is dependent on the last increment, then we use a single control and the rotation, because here in this case we use a rotation because we have two realizations in this example. If we had a process that's dependent on the last two steps, we would have a two-controlled situation. If we want to encode the realization, what we use is controlled operations on a so-called data register. We call this here squared control on UL. L is the step of what we do right now. This was step 0, 1, and 2. Now we have also 1, 2, 3, and n. Each of them is further decomposed into controlled single unitary gates. And if we put a right value or a right unitary into V, we can have specific behavior that is being beneficial for our purposes. So this is actually twofold. We have one part that encodes on the index registers, as we call the probability density function, and then on each level controlled we have these unitary V's. And we were going to show in the next step how to choose V's in such a way that we can do a meaningful measurement. So as just indicated, when we use the Z rotation with an angle 2xv, v is going to be some real number, and our psi naught will be just the plus state. Remember what we just talked about is that here, if the v is correctly chosen, our u's that were parameterized by the path would look like this here. So now we would put in xn jn up to x1 j1. Now the final state that we will have when we're finished with this is here going to have the probability density function or the square root of it. And here, as I just mentioned, is the relative phase where just there's a prefactor v, and the s would be the sum of xn jn plus and so on x1 to j1. The measurement is done on one single qubit, and that will yield the results that we need. So if we use a sigma x measurement, we denote this here as free parameter v, then we do eventually get the expectation value of cosine vsn. And likewise, when you use the sigma y observable, we get the expectation value of sine vsn. So already here we can see the very interesting dynamics that we can find by measuring an expectation value. So indeed, by having the expectation values of both observables, we can calculate the characteristic function, as we seen here. We can now choose v's as being part of 2 pi I over p, of some sort of a periodic function that we'll later do, and we have a cutoff. This can have applications. For example, if we have a Fourier series of f, we can cut off at a certain L and can now approximate the expectation value of f of Sn. So what this means is that we have shown that there is a possibility to use a quantum computer to approximate a characteristic function. That's quite interesting from our perspective. We want to work on this a bit more. Now, if you remember just the equation that we showed there, which means is when you have different functions f, you will have other Fourier coefficients CL. So now you can kind of variate the functions that you are interested in. There are very interesting applications that can be very beneficial once you have the characteristic function approximated. This seems to be interesting, but the big question now is how efficient is it and how many advantages can we actually get from this? So speaking of advantages, we note that to calculate a characteristic function is interesting in its own right. Also, the construction of the random variable in particular, the probability density function, is very versatile. And what I have promised you to show is the fundamental estimation process is the Bernoulli trial. Why? Well, the Bernoulli trial explains basically how the statistics of the Pauli X and Pauli Y observables actually behave. And that's the right modeling here in this case. So when n is the number of shots of our experiment, the error of estimating it would be just L over square root of n, essentially. Well, and as we do a measurement on one single qubit, the experimental validation on a NISQ device is actually possible. I will show you this in a moment. Also, we have shown that amplitude estimation is possible and reduces, as it is supposed to be, the estimation error to less than 6 times L over m, where m is the number of algorithm calls. All this is true for any random variable, regardless of its variance, and it's due to the quantum brute force approach that we use for stochastic simulation. It is not always true that this approach will yield better bounded variance than Monte Carlo would do, in particular because of the approximation of the Fourier series, which is cut off at L. L is part of the error and thus will also have will also grow as L goes up, of course. But for certain stochastic processes, this is going to still be better than Monte Carlo simulation on a classical computer. We want to show experimental validation on the IBM Q quantum systems that are publicly available. As an example, we used the correlated random walk, which is a little bit more non-trivial than the random walk. The specialty of the correlated random walk is that there are persistences. So when it goes in one direction, it is either more likely or less likely to go in the same direction. It is dependent on its last increment. And one of the circuits that could implement this have already been shown in a prior slide. What we can see here is that while still lots of error exists, that the principal dynamics of the characteristic function in both the real and the imaginary part match pretty closely to the theoretical values. We claim that thus the theory is right and that with better systems we will observe the correct behavior. Even though this is still far away from what we want in both size, significance, and quality, I was very excited when I saw these results because it showed that in principle this idea is valid and it works. With that, I would like to conclude my presentation today. I would like to take this time to thank my collaborators. Progress is a joint effort. We are not going to get there alone. Now the next stop I would like to have is the question answer sections. Please leave questions in the comments section. Thank you so much for listening in to my presentation about our work on stochastic processes in quantum computing. I hope it was interesting and I wish you a very nice day. Thank you so much.